Hi, everybody. Welcome. Welcome to this different scheduled Thursday that we have. Hoping we're all in the correct class. We're in period one, pre-calculus. And sorry, let me just make sure I am letting everyone in who I should be. Okay, awesome. Welcome, y'all. Let's go ahead and jump into our math class check-in. And it is actually January 21st. Yes, the day after inauguration. So just so you know, it's January 21st. Sorry. It's because I gave this lesson yesterday to period three. That's what the date there. But anyways, our check-in question today is how are you feeling right now? In general, just how are we feeling? And we're gonna go ahead and put that in the chat. Some of you might be tired. Some of you might not be tired. Some of you maybe are energetic. In general, just how are we feeling? All right, I see the chat is popping there. Let's see how we're feeling. Let me go ahead and check the. All right, so let's see. Because we usually, I think, meet in the afternoons, I think, in this new schedule. So good morning, I feel good. Feeling great. All right, we have a bunch of goods. We have some tired, feeling okay, positive, happy, ready to finish this week strong. Awesome, decent, tired, want to go to sleep. Good, I'm okay, normal. And I feel relieved. Yay. I also feel relieved, I feel like yesterday was good. I was like so nervous about yesterday. All right, I feel all right. Awesome. Okay, so now's the time so I could double check our attendance. Let's see. Again, I apologize if you did, answer the check-in and I missed you. I'm just going ahead and scrolling again, making sure. Okay. So this is who I'm missing. I'm missing Tyree, Dennis, Janet, Jorge, Henry, Alicia, Marjorie. Mm, no, I think said Lolly, you came in, right? And then Bianca. So that's who I'm missing. So again, if you want to make sure you answer that check-in question, so I could double check. Yeah, so Lolly, you're here. Am I missing Bianca? Yeah, I'm missing Bianca. Um, Marjorie, Alicia, Henry, Jorge, Janet, Dennis, and Tyree. So that's who I'm missing. If you're friends with any of these folks, feel free to send them a text to come into class so we could get our credit. Yay, we just got Janet. Go ahead and update that. All right, cool. Thank you so much for that, temperature check on how we're feeling. Again, some of us maybe are tired. I'm like sleepy too. I'm sleepy, but I'm energetic. So I'm sleepy, but positive, energetic. I'm filled with good vibes right now. I'm hoping it continues throughout the day, especially because in advisory, we finish with affirmations, and I'm still holding on to those. They're so powerful. Okay. All right, y'all. So this is our agenda. So we just had our attendance check. We're going to be continuing that activity that we started in last class. So I believe this was on Tuesday that we first started this activity about revising, and y'all were looking at two student responses and doing similarities and differences. We're jumping back on that. And we're going to finish this activity. After that, we're going to talk about the motion of a ball, and we're probably just going to get started on that lesson, and then our checkout. Okay, so asynchronous number six. Today's Thursday is due today. I do want to make a little note about asynchronous number six. A lot of people are kind of a bit afraid of it when they look at it, because it's not a Khan Academy practice. It's more like, let me open it so I can show you all. So this is what asynchronous number 6 looks like. This one is due today. I still need to input, I think, asynchronous number 5 probably into our grades. Here we go. Let's go to instructions. So it looks like this. Kind of like a word problem application-y. What I want you to do is just try your best on this though. So a lot of you maybe are like afraid when you see something like this. It kind of looks like something like a mini final, but this is not the mini final. This is kind of just getting you some practice into using your thoughts to apply our learning into a task. So you have like a table. It's going to ask you to kind of estimate how fast a cup of coffee is cooling down. And this guy here, Shane, he likes his coffee to be below 160 degrees Fahrenheit. So you're just going to try your best when you're answering these. Again, don't stress it or sweat it. Don't be like, oh, I don't know how to do this. Just try your best. I just want to see what y'all know. So that's a note on asynchronous number 6. This is what it looks like. And again, just try your best. This is participation credit homework. It's not accuracy homework. So I just want to make sure you know that. And I also put a little note here on top of the asynchronous number 6 too. So let's see what's in the chat. And no, yeah, so I don't have office hours today, but you all are to text me with any questions, and I'm happy to also give some feedback on homework as well. If anyone's dying to have some support, I'm also always available through Remind. You can send me pictures, all of that. All right, so we have Henry's here. Who else just came in? So I got you, Henry. Anyone else just came in so I could update the attendance? And Marjorie, right? Marjorie's here. And Bianca. Cool. Let me know if there's anyone else. Went ahead and I updated who just came in. Cool. So yeah, just a little note on asynchronous number 6. Don't stress it. Just do your best. We might even bring this back into class and we could talk about it next week. So just a little note on that. But if no one has any questions, we're going to jump back into that activity. So let's see if anyone has any additional questions. All right. Let's go back into that activity that we started on Tuesday. Let me refresh you on what the activity was first off, right? It's been a day. So y'all did a similarities and differences, and what I'm going to do is I'm going to debrief the task and kind of give you like what were the common misconceptions about this task. Next, I'm going to let you all know what does make good math justification. It's going to be stuff that I'm looking for when y'all do get started on the mini final. Then after all this, and we discuss what makes good math justification, you're going to be filling out a Google form where you're going to look at a student sample piece of work and you're going to try to revise their response and improve it. And that's going to be the end of this activity. And then we'll transition into the next part of our unit, which is going to be average rates. We're going to jump back into average rates after this and lead us into our mini final. Okay. So that was the activity. And then the why. The activity is designed to improve your justification. And throughout this activity, just think about what makes a good math response. And as a reminder, this was the sample piece of work we were looking at. It was from asynchronous number 3. You were given a table and the scenario that a baseball was hit, X represented seconds on the table, and H of X represented height in feet of the ball. Then you were also given that Brenda is able to catch the ball at this specific position, 3,6, if she jumps high enough. And I gave you all some time to first look at this if this is the first time you've seen it, and to kind of just remind yourself of it. That's just me rehashing what we did. And then this is where we left off. So let me go ahead and put this link back in the chat so you can remind yourself of the 2 pieces of student work we looked at and the responses you gave. as to your thoughts on it. So there it is, back into the chat. I'm going to also open it with you. And to remind you, these were the two different samples we looked at. And I wanted you all to focus on the response for number 4. So checking the reasoning on whether or not Brenda caught the ball and the different things these two different students had said about that and how they reasoned and justified it. So awesome. I see a good amount of us in the document. So definitely everyone should come into this document to refresh ourselves very quickly on what you wrote, on what the student work looked like. And then once you're here, just go down and look at what student responses and what they're seeing, and also refresh yourself on your thoughts on what you saw. And again, one thing that came out when we were like taking a look and analyzing this work is that a lot of people thought sample 1 was kind of like more elaborate is what I see, like more elaborate, somehow feels like it explains more, whereas a lot of you thought sample 2 kind of had more concrete math in the response, because their point 20 here references what they got from number 3, whereas number 4, the sample 1's response was kind of more general and did kind of make a connection to the limit, like one of our big ideas. So those are just the things that I noticed that y'all were saying down here in the document when y'all wrote. Let me give you some time to, again, refresh yourself on this. And we have about 13 people on this document. You can also feel free to take a look on my screen, just to refresh yourself. All right, awesome. All right, so I'm hoping y'all had some time to refresh yourself and take a look at what you wrote and what you thought, because now it's gonna be coming up to the debrief. So but I want to also point out, everyone, that both of these samples, some of you will notice this, but both of these samples believed that the limit does not exist. So, for example, this student says the limit doesn't exist because there might be a left and right might not meet up if they were placed on the graph. So they're saying that these two sides might not meet up. And it would make sense why someone would think that, right? Because there's missing numbers here. So they don't know if it meets up. But if you're talking about the motion of a ball, we know that the ball can't just disappear out of nowhere and then just pop up on the other side. The ball kind of has to keep going. So we know that it can't just, have some blank spots right there. It has to meet up somewhere, right? As far as the limit is concerned, when it's the motion of a ball. This student says the limit doesn't exist because the number should be 6, but they're saying it's 6.20, so therefore the limit doesn't exist. So those are just some things to think about as well as we debrief this task. Okay, so let me give you all the answer here. So I will say this, the answer for number 2 is that the limit actually does exist here, everybody. So the limit does exist. And let's go ahead and talk about why. So I'm going to go onto our slides, and I did post today's slides, by the way, on our Google Classroom. It's on my stream right here. It's Q3, day 6. We're doing revisions plus rates of change. And this is where you want to go to if you want to follow along with me. I also have all our links and stuff. Let's talk about this problem in our debrief. All right, so let me tell you all something. So when I first did this problem and I saw that Brenda was at 3,6, I wanted to say that this should be 6. I wanted to say that this is going to be 3,6 because I kind of want Brenda to catch the ball. But I can't say that actually. So let's go ahead and talk about this. So The positional motion of the ball, we know, has no gaps or breaks. The movement of the ball, we say, is continuous. It has to like be somewhere at some point in time. It can't just disappear. So the ball's eventual position can be approximated by using limits. So this is how we're applying the concept of limits to kind of like a real world scenario. Like if we know this information that it's around here, then we could kind of approximate where it would be at a certain point in time. So we can make that prediction using limits because we know that the ball's motion has no gaps or breaks. It has to like keep moving through space. Next, according to the information that we have, the limit from both sides is actually approaching 6.2. So let's talk about that because there was two different answers that I saw coming up in the homework. It was either that the limit was 6, the limit was 6.2, or that the limit did not exist. So that was like three different things I've seen. So in order to determine whether or not a limit exists, you want to refer back to our big ideas. One of the big ideas is a limit exists when the left-hand limit is equal to the right-hand limit. That's all we need to check. So let me go ahead and do that. We use a marker. So first off, I noticed that on the X values, we're approaching 3 from the left-hand side. This is the left. Their values are less than 3. And we're also approaching 3 from the right-hand side. These are all numbers that are greater than 3, but really close to 3. Okay. And next off, we're going to look at the Y values. So think of h of x kind of like our Y's, the heights. So from the left, it starts off at 6.228. Then it goes down. So it's decreasing to 6.210 to 6.202. And that's all the information we have. We have blanks here. Then from the right, we have 5.9, 6.14, and then 6.198. So if you take a look here, according to the table, the values on the left, the Y values on the left are kind of approaching 6.2. And if you look down here, it's also kind of approaching, look at this number, it's really close to 6.2. So because the left-hand limit and the right-hand limit are approaching the same thing, 6.2, the limit does exist. And how I would write that formally, of course, let me do that down here. The limit as x approaches 3 from the left of, and my function is h of x. According to our table, we see that it's approaching 6.2, not 6. I wanted to say 6 too, by the way, and I did say 6. And I actually changed my answer after I looked at, after I looked at your work. And that's actually what I want you all to do. It's like you look at other people's work and you're adjusting your answer based on what you're seeing. That's all about the learning process. That's how we make sense of things and learn. So the left-hand limit is equal to the right-hand limit. So that means the limit does exist. And we could even drop the plus or minus and just say the limit as x approaches 3. So limit exists. And the limit is going to be 6.2. That's actually our limit. So because this is a real world situation and we know that you can't have a hole in this graph, right? There's no holes if you're talking about the real world. The ball just can't disappear then reappear. That means that the limit value has to be that at around 3, we have 6.2. That the ball is going to be around there at x equals 3 seconds. So that's the reasoning that's going into here. So the limit does exist. And according to the data that we're given, we're approaching 6.2. We're not approaching 6. In fact, if you look at the table right here, your 6 would be between here, 6.14 and 5.9. That's where 6 would be. And again, I made the same, I thought it was 6 though, because I wanted Brenda to, I wanted the ball to be where exactly Brenda was at. Okay. So then 3, 6 must be the position that Brenda's at. And at three, that means at 3 seconds of the ball's motion, she can jump high enough to reach 6 feet, is what the information we were given. And what did I do is I would basically, like, because I was kind of like making sure I'm not confusing the limit with Brenda's position, I went on Desmos and I graphed the data points. And I also graphed in a different color in black right here where Brenda was at. So I kind of just created an additional model to help me see what's happening. So in green is kind of like the ball's motion here. And this is where Brenda would be at. So one could actually argue that she catches the ball or not. It actually depends on your justification. So let me explain that. So I'm gonna delete this for a bit so I could kind of show you what I mean by that. So I'm gonna go to my Desmos. Yeah, so you maybe want to make a note on why it's 6.2 on your slide, by the way, why the limit would be 6.2. Let me clear my drawings. And you all can have you have access to this bottom notes part where I put the Desmos right here. Okay, so this is the strategy I did. So because it was hard for me to kind of differentiate where Brenda's at, where my ball's at, I went to Desmos and created a visual for myself. So I put the same table we were given. We know that we don't know what's happening around 3, but we can use limits to make an estimation. We could say that the ball would be around 6.2. I don't know where that point went, but that's 6. So kind of near there somewhere. It's probably in between these 2 points because it's really close. So basically the ball's going to be around 6.2, but Brenda says if she jumps high enough, she'll be right here. Here's the thing. This is why you can argue whether or not she catches a ball and you'd still be right. The reason for that is that, okay, this problem is a little bit ambiguous because when you say she could jump um, and she reaches 6 feet, are we adding in her arm, like her arm extending and reaching up, or are we not? So the difference between where Brenda's at and where the ball is at is 0.2 feet. That's about 2 inches. So you could basically argue that she will still catch the ball because 2 inches is that not that far off. Whereas some people might say 2 inches is a lot and that she'll miss the ball. It kind of depends where she's at. Is her head at the 6 feet? Is her hand? So this is why this is actually very open. And you could say that she does catch the ball or she doesn't. Depends on your justification. Let's see what's in the chat. How tall is she? So that's something we don't know. If you look back at the problem, right? Let me show you. If you look back at the original problem, all we're given is that she's able to catch the ball at 3,6 if she jumps high enough. So think about this in the real world. If you know someone's in the field at around 3,6 and you know the ball's heading there and that the ball, she could jump high enough to reach 3,6, which you catch the balls. And it's ambiguous because we don't know if we're talking about, like, when they're saying 3,6, is that where her head's at? Is that where her stomach's at? The 2 inches, maybe her arm could kind of make up for that difference. So there's different ways to interpret this problem. And your job is to justify whether or not she catches the ball using the math that you've made or using our big ideas, both if you want to make it even stronger. So again, it totally helped for me to kind of graph it and see visually what's happening. And to also notice, wait a sec, so she's right here and she's only about 2 inches off. Can't that literally be like an arm extension? But I do have some students who are like, nope, she will not catch the ball. And they have a specific way they're interpreting it. And they could totally be right, depending on their justification. So again, this is open-ended answers. So one can argue she catches the ball or not, and it depends on your justification. So that is my debrief for this. And here's some common pitfalls that I saw. Number 1, some thought that if Brenda didn't catch the ball, it meant the limit didn't exist. So that was something common I saw in the homework. Some were saying like, okay, Brenda does not catch the ball, So then the limit is DNE. That is incorrect. You need to go back to our big ideas. The limit exists if the left-hand limit is approaching the right-hand limit. That's the only thing you need to pay attention to when it comes to whether or not a limit exists. And the ball's limit has to exist because the ball's motion is continuous. It has no breaks or gaps. So that's something to pay attention to. Another common pitfall I saw is that some assumed that Brenda must catch the ball and that the limit has to be 6. And let me tell you, I did the same thing. So I was saying this has to be 6 because Brenda has to catch the ball. And if you look at your data table, that's not what the limit is approaching, right? The limit here is distinctly approaching 6.2 from the left and the right hand side. So that was a common pitfall. Does anyone have any questions about our debrief before you all get to revise a response given all this information? So again, this is open-ended. You can argue that she catches it or not. I'm just looking for how you're justifying it. And then, by the way, Janet, I like how you asked how tall she was, because you could even put that in your response. Like, if she's this tall, she'll catch the ball. If she's not this tall, she won't catch the ball. So that's something you could totally incorporate in your justification. You're considering the different factors that come into this problem. That's why this is so open-ended. Definitely like that question. Okay. If there's no questions, everyone, here's what we're going to do next. We're going to, well, first I'm going to tell you what is good math justification, and then you're going to try to show me that. You're going to revise the response. So first off, interpret and analyze the problem. I saw both of the 2 student samples that we looked at today, interpreting and analyzing. So they tried their best to kind of relate their math to what's happening in the context, the real world. You definitely want to reference either any math models or create models. So notice how I had to go separately on Desmos. I created a model to visualize the situation. So that is a math strategy. And or reference your table, right? So like that's student number 2, the student work we looked at, she was referencing the table. She or he was referencing the table when she said 6.20 and that the fact that Brenda was 0.20 off according to student number 2, right? So they're referencing a model or a table. That's a key skill. Cites evidence from context. So not only are you referencing your table or your graph, you're also referencing your context, like what's happening in the actual situation of the problem. That's when you consider how tall Brenda is, whether her arm extends, the 2 inches that she's off, does that matter as much when it comes to the likelihood of catching the ball? So connecting the math to the situation. So cites your evidence from context. And then lastly, apply big idea. So knowing that in this problem, you actually need to use limits to reason whether or not she would catch the ball. So I think student number 1 did that. So they referenced limits when they were talking about their answer. So that is what makes good math justification. And that is what I'm going to be looking for, especially in the mini final. And that's why we're already getting a head start and talking about this. So that's what this is. You should have the slides open so that you have this next to you when you're doing the form. Again, I'll wait to see if we have any questions. All right. If any questions pop up, just let me know. So what I intended for is 8 minutes on this portion. Let me go ahead and give you the Google form, or maybe some of you, if you open up your own copy, you have it if you go to slide number 9. And I'm going to also put it in the chat though. I'm going to first go ahead and talk about it. Once everything's cool, we don't have questions, I'll start the 8-minute timer. And this will be for credit on Power School, and you don't have to worry about it. So I know yesterday when I did this lesson, some students were very worried because they felt like they didn't really understand the concept that we had going on, and that's totally fine. So if you're like totally confused about how to give good feedback and or how to revise the response, you could go ahead and just put some questions you have. Like what further questions do you have or do you need in order to try your best to give some feedback? So that's just some, to make sure, don't stress about it right now. Um, so when you open this up, you're gonna, of course, put your email address so I know who you are. The next thing that's gonna happen is the first question is, what feedback would you give this response to meet the criteria for good math justification? Now, I think this is student sample number one. You're gonna now give feedback according to slide number 8, what we said was good math justification. You're going to try to offer some feedback to this student, and you're going to put your feedback down here. After you go ahead and offer some feedback, you're going to try your best to revise and improve the response according to that student sample above. So you're going to try to rewrite this response and try to improve it. And then that's going to be the end of it, and you're going to click submit. Does anyone have any questions about the Google form or our directions right now? Okay, if we don't have any questions, I'm gonna go ahead and have you all get started. Let me X this out so I could put up our timer. Again, reference slide number 8 for what makes good math justification. You can also reference slide number 7, where I kind of talk about what were the common pitfalls and what the limit was and why. So you could totally reference that. You can even reference the little Desmos link I put there. But if all else is good, let's go ahead and start our timer for 8 minutes, everyone. I'll be here for any questions. Everyone, I see a few of us are still working, so let me go ahead and add 3 more minutes to this timer. Add 3 more minutes and then we'll come back. All right, everybody, welcome back. Definitely finish up your response on this. Definitely just looking for what your initial thoughts are on how to improve the answer and what your revision would look like if you were to the one to rewrite this answer to the question. So definitely make sure you submit that. We're going to go ahead and transition into the next thing. And thank you so much for your thoughts. I'm so excited to see the revisions that you all are making to the response that we were looking at. All right, here's our transition, everybody. And oops, here's what we want to think about before we transition. So now we're moving on to um, determining how fast an object is going at an exact instance. And I want you to think about how is the slope of a function connected to like speed and or rate, if it helps you think of it. Um, So this might kind of relate to what you're going to be doing in the homework, right? You're going to be asked to kind of figure out at exactly 5 minutes how fast is the coffee cooling down. It's basically what you're going to be asked to kind of do. But again, don't stress it. I just want to hear your thoughts and ideas on that for asynchronous number 6. And this lesson is going to continue on into next week, Monday. So, so we're not going to finish this today. We're just going to start it. But these are some things to think about. So, how can I determine how fast an object is going at an exact instance in time? And how is a slope of a function connected to speed or rate, right? We could also connect it to any rate. Okay, so for this next lesson that we're going to continue and finish on Monday, we're going to start thinking about today. We're again talking about balls being thrown. So you have a ball being thrown. This is its motion through space, like a parabola. It's thrown upward and goes down, hits the ground. And then I just clicked 2 random points. You have this ball thrown, and I want you to notice that on the y-axis, you have the height of the ball in meters. And on the x-axis, you have its time in seconds. Now, what if you want to figure out how fast the ball is going? The question is, what can we do? Now, do not answer in the chat. Our participation that's going to be for today is going to be on a Padlet. So I'm going to go ahead and put the Padlet in the chat. Or if you have a copy of the slides, they're in the notes section. So you just go down in the notes section and click on the Padlet where it says period 1. And once you open up the Padlet, you're going to already see a bunch of the questions I'll be asking you in the upcoming periods once we hit there. But I want us all to be in the opener question number 1. This is the first column. So again, I have the picture and I have the question. Imagine you have a ball thrown and it's heights in meters and time in seconds, and you want to figure out how fast it's going. What are some things we can do? And I want you to put your ideas by adding your post as a plus. Yeah, so if you click plus like this, you can add your post. Now, if your name is not popping up, right, you definitely want to put your name like in the title position, just like Leslie's first post here. So that's what we're going to be doing here. Go ahead and take about a minute or two to put down your ideas. If I want to figure out the speed of the ball, what can we do? What are some ideas? And that's our opening question. Let me give you all some time on that. I see we're still writing, so I'm going to give us, I'll give us some wait time. So some of you can finish up. There's a lot of good thoughts there in the opener. So I'm going to give some more time here. All right, I'm gonna go ahead and take some time to read some of the ideas y'all are coming up with. I saw some good stuff as I initially scrolled. All right, so I see you have to use a secant line to find the rate of change, I think. Awesome. So we're bringing up some formal vocabulary, secant line. Maybe some of you heard that in the Khan Academy video, or maybe saw that in the Big Ideas packet. Awesome. I love that application. Maybe it has something to do with a rate of time or velocity over speed over time. I'm hoping I'm reading that right. We can try average rate of change. So I'm seeing like rate rates being mentioned and or distance and time and average rate of change or rate of change. I like how there's a physics coming in here. Gravity pulls it down at the speed of negative 9.8 meters per second squared. Now, I would say you're close, actually. Actually, negative 9.8 meters per second squared is the acceleration. That would not be the speed. And how we know that's acceleration is because second is squared. So that's just a key point there. All right, rate of change. I think you'd have to see the lowest and highest point to figure out the time. Yeah, that is a process that happens. And again, average rate of change is coming up a lot. Here, using the speed equation, distance, change in distance over change in time is equal to speed. I love the formal definition. Rate of change is mentioned. Okay, so then you can tell that in this function, the rate isn't constant, so it's not going to be easy. Maybe you have to use a different method involving the secant lines, which would be an estimate. Yes, that is spot on. Wow. I think if we use the numbers for each second, we could plug in how far they traveled. Yeah, we're going to have to use the data that we have. That's correct. All right, and then rates of change. Let's just see if there's anything different. Ooh, there's something different. I think we could use limits as well as average rate of change to figure out the speed of an object. That's some forward thinking. Yeah. Reading the graph and seeing how fast it's going. All right, look at all your ideas, guys. These are great. Wow. Let's see what's in the chat. Yeah, about the negative 9.8 meters per second square. Yeah, it's the units there that gives me a telltale sign. All right, awesome. So that is our opener question to get us thinking about this problem. Now, I guess we won't have time, right? The next thing that we're going to have to say for Monday, or some of you, you have the copy of these slides. You could just take a look. We're going to review on how to actually calculate the average rate of change. All of you who said average rate of change or speed is distance over time, that is exactly what we're going to be doing. And we will need to actually make an estimate because as, who said it, Marvin? On the post. As they said, it's going to be a little bit complex and we're going to be making estimates because the rate of change will not be constant. It's kind of always changing. So that's going to be what it's going to lead into. And yeah, let's see what's in the chat. Yay. Oh, I took notes on this. Yes, that's awesome. And again, if some of you are kind of curious about what is instant rate of change, like if you've seen that on the packet, a good way to think of instant rate of change or instantaneous rate of change is think about like when you or your parents, whatever, right, are driving a car and you look at this. This is called a speedometer. When you look at the speedometer, what you're looking at is not an average rate of change. It's actually your exact rate of change at that instant. That's why it's always changing, right? This is an idea. This is an example of an instant rate of change or an instantaneous rate of change. But we're going to go ahead and jump into that and have you all respond to this on Monday. Let's see what's in the chat. And yeah, asynchronous number 6 is due today. And again, though, a lot of you might feel like it's like, oh, the teacher did not give us steps on how to do this. Again, it's more so get your ideas down there and don't worry so much about it being correct. Yeah, asynchronous number 6 is due at midnight tonight. Again, just refer to this note that I put up here. Try your best. Don't worry about being correct. More so, just focus on how you're justifying your answers. So that's just a little tip on tonight's assignment, because we're not going to actually exactly know how to do this until we actually have the tools that we're going to be learning next week. But this is a way for y'all to already get your initial thoughts in. Let me know if anyone has any questions on that. But if we don't, I don't have a checkout question for us all. So y'all, I hope we have a great day. Enjoy today. Bye everybody. Great Thursday. Bye. It's almost Friday, everyone. We got this. Bye y'all.
Bye.
Bye.